Hello, my name is Gemma, and today I'm going to be telling you about PID code. PID code uses inputs from its environment to control the outputs of a system. For example, controlling how much voltage you send to an elevator based on its current speed and position. This is a pretty simple example that I will be using throughout the video to show how the code works. The simplest thing we could do is send some code to the elevator that says, give full voltage if you are below the goal position, give full voltage in the opposite direction if you are above the goal position, and give no voltage if you are at the goal. This doesn't work very well because it'll constantly overshoot the goal and the elevator will end up bouncing up and down, but it will never actually reach the goal. This makes for a pretty terrible ride, so we can use PID code to make it better. PID stands for proportional integral derivative. These are the three components to the code that help tune it to be a better ride. There are constants that are associated with each part, and there are many ways to manually tune these constants for each individual system, but the overall code will be the same for all systems. First, we add a value that is proportional to the error of our position. The error is the difference between the goal position and our current position. This will decrease the voltage as we get closer to our goal. This allows for the elevator to start slowing down when we get closer. However, this isn't perfect and we will still overshoot our goal. To help with this, we add an integral aspect to our code. This will increase power as the area between the two curves increases. For example, a giant is pushing down on our elevator. As time increases, our integral is going to increase at a larger rate, since our error is constant. This part of the code will add more power to push against this force and get us closer to our goal. Without that outside force, the error would be decreasing, the integral would be increasing at a smaller rate, and our code would send less power. Another situation that the integral is useful in is if you get really close to your goal, but you're just not quite there yet. The integral will push you over that finish line. Most controllers just need PI code, but occasionally that doesn't work. And that's where the derivative comes in. The derivative is looking into the future to see what the elevator is planning on doing. This part of the code will decrease the power as the derivative or speed of the elevator increases. This is useful in edge cases where the speed of the elevator is unusually fast, and the elevator is going to speed past its goal if nothing stops it. While the actual code can get pretty gnarly, the core concepts behind PID code are fairly simple, and it's a great way to show a practical application of calculus. PID code has been used historically in controlling temperatures in machinery or automatically steering ships. It's also used in high school robotics to control the drivetrains, elevators, and arms on different robots, and that's actually where I first learned about PID code. Thanks for watching, and on the screen now are the sources that I used for this video.